Hi, and welcome to Section 3, Dealing with Data. In this section, we will start off with the enter, update, exit pattern. We would then learn building an array as data, binding object literals as data, and binding functions as data. Later, we will learn working with arrays, filtering with data, and sorting with data. Lastly, we would see loading data from a server and asynchronous data loading using queue. Now we move on to the first video of this section that deals with the enter, update, exit pattern. In this video, we're going to take a look at the connection between data and its visual representation, which is referred to as the enter, update, exit pattern in D3. The task of matching each datum with its visual representation, for example, drawing a single bar for every data point you have in your dataset, updating the bars when the data points change, and then eventually removing the bars when certain data points no longer exist, seems to be a complicated and tedious task. This is precisely why D3 was designed, to provide an ingenious way of simplifying the implementation of this task. This way of defining the connection between data and its visual representation is usually referred to as the enter, update, exit pattern in D3. The pattern is profoundly different from the typical imperative method most developers are familiar with. First, let's take a look at the conceptual illustration of the two domains. Here, the two circles represent two joined sets. Set A depicts your data set, whereas set B represents the visual elements. This is essentially how D3 sees the connection between your data and visual elements. You might be asking how set theory will help your data visualization effort here. Let me explain. First, consider the question, how can I find all visual elements that currently represent their corresponding data point? The answer is A intersection B. This denotes the intersection of sets A and B, the elements that exist in both data and visual domains. The shaded area represents the intersection between the two sets, A and B. In D3, the selection.data function can be used to select this intersection. The selection.data function upon selection sets up the connection between the data domain and visual domain. The initial selection forms the visual set B, whereas the data provided in the data function from dataset A. The return result of this function is a new selection, a data-bound selection of all elements existing in this intersection. Now, you can invoke the modifier function on this new selection to update all the existing elements. This mode of selection is usually referred to as the update mode. The second question we will need to answer here is how can I target data points that have not yet been visualized? The answer is the set difference of A and B, denoted as A upon B, which can be seen visually through this illustration. The shaded area in set A represents the data points that have not yet been visualized. In order to gain access to this A upon B subset, these functions need to be performed on a data-bound D3 selection. The selection.data.enter function returns a new selection representing the A upon B subset, which contains all the pieces of data that has not yet been represented in the visual domain. The regular modifier function can then be chained to this new selection method to create new visual elements that represent the given data elements. This mode of selection is simply referred to as the enter mode. The third case in our discussion covers the visual elements that exist in our dataset but no longer have any corresponding data element associated with them. You might ask how this kind of visual element can exist in the first place. This is usually caused by removing the elements from the dataset. That is, if you initially visualized all data points within your dataset and removed some data points after that. Now you have certain visual elements that are no longer representing any valid data point in your dataset. This subset can be discovered using an inverse of the update difference, denoted as B upon A. The shaded area represents the difference we just discussed. The subset can be selected using the selection.exit function on a data-bound selection. The selection.data.exit function, when invoked on a data-bound D3 selection, computes a new selection which contains all visual elements that are no longer associated with any valid data element. As a valid D3 selection object, the modifier function can then be chained to the selection to update and remove these visual elements that are no longer required as part of our visualization. This mode of selection is called the exit mode. Together, the three different selection modes cover all possible cases of interaction between the data and its visual domain. Additionally, D3 also offers a fourth selection mode that is very handy when you need to avoid duplicating visualization code, or the so-called dry up your code. This fourth mode is called merge mode. It can be invoked using the selection.merge function. This function merges the given selection passed to the merge function with the selection where the function is invoked and returns a new selection that is a union of both. In the enter, update, exit pattern, the merge function is commonly used to construct a selection that covers both the enter and update modes, since that's where most code duplication would otherwise live. The shaded area in this illustration shows the data points targeted by merge mode that combines both enter and update modes, which is essentially the entire set A. This is very convenient, since now a single change of modifiers can be utilized to style both modes and thus lead to less code duplication. Cool! So that's all about the enter, update, exit pattern. We have learned that it is the cornerstone of any D3-driven visualization.